universe is screaming with secrets. Are you listening? Join renowned astronomer and History Channel analyst Mark D'Antonio for a journey across the light years.
We're looking at stars that died before we were born and planets that might just be looking back.
From the mysteries of deep space, live feeds from the SkyTour LiveStream telescopes, we're bringing the heavens to you. It's the SkyTour Radio with Mark D'Antonio. Look up, look up, look up, look up. The show is about to begin.
Wow. Hello, welcome. This is our inaugural show, and this is Tara Daiulis.
Hi,
Tara.
How's it going, everyone? Hi.
Yeah, she joined us fresh over from the other network like I came over, and it's very cool. I basically took the offer from Race Hobbs and from Margie K to join the UnXplained Network. It was wonderful. I mean, it's so cool, and eventually the shows are going to be all over the place, right, Tara? I mean, it'll be a lot of fun.
Mm-hmm.
Yeah, So anyway, I thought tonight I would just start off by kind of introducing to those in the UnXplained family who we are. I'm an astronomer. This is what we look like. Okay. Tara is actually in our astronomical network. She is in our nonprofit organization called SkyTour LiveStream, and she, along with Marianne Robb, who and Terry used to work for the governor of Arizona. I mean, my gosh, I'm surrounded by prestige here, so
yes,
I have to be on top of my game. And Marianne Robb was a 37-year police veteran.
Ooh, yeah,
and we all know each other very well.
7 years, wow.
Yeah, I know, and so cool. And of course, we already have a crew in the chat coming in to say hi. Al Santoriga says hi. Autopilot. We got Sam S. We got all kinds of people. Dave and Bangor, Maine. These are all people. I see Bob in Canada. C&D boy. I mean, cool guy. These are all wonderful people that are here to see us off on this new journey. We're gonna do something really cool out there because in the last stream with SkyTour LiveStream, and by the way, I should probably just say to those who don't know who are listening. SkyTour LiveStream are remote telescopes that I put in Arizona with the help of that person and Marianne.
Mm-hmm.
And in fact, Tara supervised the building of our first observatory.
Oh, that was fun. Yep.
That was in the Sonoran Desert, west of Phoenix. Yep.
In the heat.
In the heat. Yeah.
Extreme heat.
Yes. I'm familiar with the heat. It put me in the hospital that time, remember?
Yes, it did. Mm-hmm.
Yeah, I just... I should have had more of this. This is called water. It's a life-giving fluid. And I was filling in a trench that was dug for our electrical conduit out to the building. And I didn't think. And I just kept shoveling dirt back in. I had a hat on. I figured, well, what else would I need? How about life-giving fluid?
Water. You could lead Mark to water, but you couldn't make him drink that day.
And that's true. And I wasn't thirsty. And that's sort of a big warning sign.
Yeah,
when you're not thirsty, you just make it worse and worse. You don't realize it. So I got very dehydrated, and I was like crispy like a cracker, and they brought me to the hospital, and I ended up taking, I think, 3 liters of fluid or something like that. It was just a ridiculous amount in order to get my fluid levels back up.
Yeah. That's really common for people who visit Arizona who aren't used to the hiking in the heat. So
yeah, and you know what? I was actually thinking to myself, well, I'm okay. I'm doing okay, and that's an illusion. Now, this again, to be fair, this was early on in my forays out to Arizona. Now I'm a little bit smarter about all that, and live and learn, nearly die. Whatever. So SkyTour LiveStream telescopes are the one in the Sonoran Desert is a wide field system, and we look at giant swaths of the night sky, take photos live, and broadcast them around the world to everybody who watches us on our YouTube channel, which is where we're broadcasting to right now. It's the SkyTour LiveStream on YouTube, and you can look it up. You'll find it. And the with UnXplained Network, we're going to Rumble and a bunch of other social media platforms as well.
Awesome.
And it's really cool. And I heard rumor that we're going to be on another network as well, simulcast, but I don't want to say anything. I did put it in the text. But anyway, so one telescope just wasn't enough because that was a wide field system. So we ended up with a benefactor who gave us some donations. We bought a second telescope, and with our Patreon subscribers, which we just are so grateful for, they've helped us. We only have a handful, but it's enough to pay the lease on another observatory 200 miles from the first. And that telescope is a narrow field magnified system. So, I mean, you're like, okay, what are we going to see here? I mean, we're looking at a much more close-up field with a lot more detail. And that's what helps us see the detailed objects. And that's down in Benson, Arizona, on a plateau that we're sharing with like 9 other professional astronomers. And that's kind of cool because you're surrounded by observatories there, and nobody bothers you, and you can do all the work. Now, how do I do this work? I live in Connecticut. Do I fly out every time I want to stream? No. I run these observatories right from this very seat in Connecticut.
It's amazing.
It is kind of cool. I mean,
it's amazing.
I spent a couple years trying to figure out the best ways to do this. I wrote software to do the housekeeping stuff, like take the roof off the building. It just slides right off. And then, run the telescopes and get the telescopes up and running. And then I used other software to control the telescope and to take the pictures. And that's really cool. So we've been going since I think 2016 now, Tara. It's like a long while.
Oh, time flies. That's fabulous, though.
Yeah, it started. It started on the front lawn here.
In your little dome,
I had an actual observatory dome in the front lawn. It was the only one in town, and that telescope is right behind me. You can kind of see it right there.
Yeah, barely, but yes.
Yeah, it's right there.
There
It's
it
a
is.
little dim. And I moved it in here to rehab it, and we may do something with that or not. I'm not sure. But we're going to put a telescope back in the East Coast as well, and I think it's going to be a solar telescope to study the sun.
So neat. Yeah.
That's cool. So tonight, what we're going to do is something that I started doing with the regular streams and with the observatories, and that is look at the universe as a time machine. So when we look at things in the universe, when did that light leave that object to get here?
Okay.
And then after it left that object, how long did it take to get here? And during that time, when it left the object, what was happening on Earth at that particular point in history?
Cool. Interesting.
It shows you the time frame of the universe, and it shows you how the universe is so big. And quite frankly, light moves so slow, all right? And it's the fastest speed in our universe, but it's still slow. And you'll see what I mean as we get going. I did want to say hello to everybody in the chat. I already did say hi. And people are saying hi to you too. Actually, that's nice. Yeah. So we got a lot of people, a lot of followers that just love what we do, and I'm just so happy about this. So and I think that's kind of cool. All right. So this is the talk that I want to show you tonight.
Oh, that's so cool.
Yeah. Now we photographed that object. That's actually called the elephant's trunk.
Elephant's trunk. Yeah.
You knew that.
Yeah.
Yeah. And so what I ended up doing was putting together this little talk, which gives us an idea about what was happening on Earth in history when these objects light left them when the very beginning to get here. Okay, so without further ado, I want to keep going a little bit. Now, light speed is the speed limit in our four-dimensional universe. That's X, Y, and Z moving through time. Okay, that speed limit's pretty fast. Okay, when I know I just told you it was slow, didn't I? So what
You
do I
did.
mean? I did.
Hmm.
Well, it's slow considering the size of the universe, and here's why.
Okay.
When you look at the universe and you look at things that are distant, the light left those things a long time ago, right? And to put that in perspective, that's what this talk is, all right? So light moves at a speed that's 186,282 miles per hour. I'm sorry, miles per second, okay? So that means that light can go 7 times around the Earth in 1 second, okay?
Wow.
Yeah. So that's a lot, all right? Now, even at that speed, it still takes light some time to get here from the objects, and we'll talk about that, you know. Now, every single object, this is why the universe is a big time machine. Every single object we see in the universe is as it was, not as it is. And that's something that's also fascinating and that we need to consider and think about. All right. So, the idea of what happened on Earth when the light started on its journey from deep space is a good one because and the knowledge is interesting because it tells us how the universe has evolved over time, and these objects have always been there throughout our history in some cases. Okay, and in some cases we weren't even here when they began their journey. I mean, that gets even crazier. But anyway, let's just start off. Okay, we love the moon. All right. This photo we took of the moon real quick. It's 240,000 miles away. Now, it's literally takes 1.3 seconds for that light to get here from the moon. And that means you probably went and took a breath. So you took one breath and moonlight from the sun that reflected off the moon reached you at that point.
Okay.
Now, how do we know how fast it takes light to get here? We need to know the distance that the moon is. And for that, during the Apollo missions, and yes, we went to the moon. Don't give me any crap about that. Okay. Not you, but I mean.
No, I know.
Yeah, I know.
There's people who think otherwise.
I know there are. And it's amazing how many people that can be. But when we look at the distance to the moon, the way we calculated it goes back to a device that was created at the university where I got my astronomy degree. All right. And it was called the Lunar Retroreflector, experiment. And it was composed of a rectangular array of tiny little prisms. And they're set up like reflectors on a car. Now, those types of reflectors are called corner reflectors. And so no matter which way the light hits them, some of that light's going to come back toward the person looking at it. There will be a piece that will always come back to whichever direction you're looking at it from. That said, when the university made these, they gave them to the Apollo program. The Apollo program put them on the moon. And so from Earth, we typically will send up a green laser, argon laser, to the moon. And by the time it gets to the moon, the laser beam is about 4 miles wide. Okay.
Wow.
And and it's just about 10 miles wide when it gets back. However, the little bit of energy we can detect with the detector will tell us enough of the information we need to know. What we need to know is how fast it took that light to get here. Okay. So if we beam the laser out at a specific point in time, all right, we know that 2.6 seconds later, we're going to see that beam come back, although it's going to be 10 miles wide, roughly, just over, just under. So that gives us the distance because we can figure out from that distance, knowing how far the moon is, we can kind of roughly guess how fast light moves. Okay. But there's other experiments to determine that. However, what's interesting is that in that time, we've only taken a breath, right? Now let's move out a little further and let's go to the sun.
Okay,
Right?
pretty.
Yeah, here's the beautiful sun. This is in the light of hydrogen alpha. we're seeing through all the brightness, and we're seeing some of the details on the semi-surface of the sun. So that takes 8 minutes. So if the sun disappeared right now, we would not know for 8 minutes if it was daytime. Okay. And if it was nighttime, we might not know for a lot longer until someone called and said, hey, guess what? The sun went out. I used to do a talk called What If the Sun Went Out? And it talks about how Earth would change over like 7 days. Because you know how they say, well, the Earth was created in 7 days, right? Well, over 7 days, the Earth would end up being destroyed.
Wow.
And all life would be extinguished. There would be no atmosphere after 7 days. The oceans would be completely frozen over. And we'd be a glacial ice ball in space.
Snowball.
After just 7 days, Tara.
Wow.
Just 7 days. Yeah.
I would have thought it would have taken longer, but I didn't realize the atmosphere would go.
Oh, yeah. The atmosphere, when it got really, really cold, the atmosphere would rain out like snow. You'd get, of course, the carbon dioxide would probably go first, and you get snow, but it'd be carbon dioxide, ice, dry ice. And then you get nitrogen and other stuff, and it would just fall out of the atmosphere and basically leave us without an atmosphere. So by then you're dead. Anyway,
no, we'll be underground, right?
Well, where are you going to get your oxygen unless you pipe it in, right?
Yeah, well.
Then you'd have to manufacture it when you're out of it.
Well, that's what we plan to do on Mars, right?
Actually, on Mars, we're going to make it from a device called MOXIE. Now, the Perseverance rover, that's a very good question or good comment. Because on Mars, the Perseverance rover did an experiment where it had a car battery sized MOXIE experiment. What's that stand for? Mars Oxygen In Situ Experiment. All right. And MOXIE's idea was Mars' atmosphere is all carbon dioxide. So let's see if we can make oxygen out of Mars' carbon dioxide atmosphere, because carbon dioxide is carbon and 2 oxygen atoms, CO2. Well, we breathe O2. So can we separate the O2 from carbon? Well, not directly, but we can. And the MOXIE experiment performed that, and it worked admirably. In fact, it made more oxygen than they thought they might get. So I foresee sending up inflatable habitats on Mars. Now, I call them inflatatats. Okay. So they send these inflatatats up to Mars long before people ever get there. They start them up. They have sensors that can send back telemetry saying, yep, here's they're set up. Everything's fine. No leaks. And then they start processing with gigantic MOXIE systems. Now, the MOXIE system on the Perseverance rover is the size of a car battery. Okay. Yeah. But a MOXIE system the size of a truck might be able to fill a dome, or 2 trucks, So you'd have to ship up a MOXIE system, have it fit inside a rocket, have it land safely on Mars and deploy and start operation inside an inflatatat. So they could literally have a cold but oxygenated atmosphere inside of one of these inflatable habitats.
How cool.
Yeah. Then the next thing you'd have to do is heat it, and they'd have to find a way to heat it. They could use solar heating of some type. They could also use RTGs, they're called radio isotope thermal generators. They generate heat just like for the Cassini mission to Saturn and Perseverance itself, Curiosity rover. And these things are just amazingly good at what they do. So they could provide power and thus heat that might be able to heat the habitat up to, say, a comfortable 65 degrees.
Perfect.
Yeah, right. So now, then we'd have to have water, and then we'd have to have food. And so it is. So what would happen is they would robotically collect ice from the planet, and which is literally, there's so much ice, water ice on that planet, that depending on where they land, it could literally be right under their feet. And they could just dig it out of the ground, bring it inside, melt it, and literally create a whole ecosystem inside this inflated tap. It'd be the coolest thing, right?
Oh, yeah.
Yeah.
One-way
Yeah.
trip, though, right?
Um, maybe. I know a lot of people though that are willing to do that, and I'm just not, just not excited about that. I wouldn't go. Wouldn't go. You know why? I couldn't run my observatories from Mars.
Oh, it's a little bit too much to ask, huh?
Yeah, you know why?
Yeah.
Because it takes at its shortest, it'll be 4 minutes to get a signal to Mars. Okay. And so if I was to run it from Mars, 4 minutes it would take to get the signal, move the telescope just that way a little bit. Gotta wait that long. And the longest it's about 22 minutes.
Oh my
So
gosh.
you know,
Probably
no
wouldn't be
fun.
worth it, right? Yeah.
Nah.
It'd be fun though.
Impractical.
I might go if I was asked, you know. I think I might contemplate going, so
Without being able to come back.
probably. If I could sneak a cat or something on board,
Oh,
that
there
would
it
be even
comes.
better, you know? So
Sneak a cat on board. Yeah,
yeah.
and then, a few years later you might call NASA and say, "Could you ship up another cat, please?"
Yes.
Yeah.
Oh,
Now, our sun is a star that's called a G2. You see that there, and the letter
yeah.
G followed by the numeral 2. Now, we have we have a bunch of classifications that we have for stars, and the classification follows a pattern that relates to temperature. This is the classification graph right here.
Mm.
Along the left side, you see right there, you see that the temperature on the left side and the, the luminosity, the brightness. And along the bottom, you see the temperature. Now, why is that temperature? It looks like letters. Yeah, O stars are the hottest and bluest stars. Okay. And blue, by the way, is deep blue is the hottest color in the universe. And B stars are the next hottest. A stars are kind of white. F stars are kind of yellowish, whitish yellow. G stars are kind of whitish yellow, a little more toward the orange near the end. K stars are orange, and M stars are red. Now you notice this line here, this line going through the middle. It says main sequence right there.
Mhm.
Okay. Well, the main sequence, these are all what we call normal stars, stars that are fusing hydrogen into helium. Yay. That's the fuel that our sun uses. In fact, you can see our sun right there in the middle. It's the yellow one. If you look right around here, it looks like a 1 right there on the
Yes.
left side. Well, if you draw a line across, you'll intercept the word sun, S-U-N, because this is all relative to our sun. Okay, so we have stars that are literally 1,000,000 times the intrinsic brightness of our sun,
Wow.
and stars that are literally 1,000th or 100th of the brightness of our sun at the other end in the red. So as those stars move down the main sequence, the temperature goes from extremely hot to a little bit cooler until it's cooler and cooler. Now it's still hot. It's still
Right.
very hot. Okay, the deep red stars at the very end of that list, they might only be slightly larger than Jupiter because they get smaller when we get down that way. And however, that deep red that they are is a color that relates to their temperature. The hotter they are, the bluer they are. So that red stars at the back end there, they have an interesting characteristic, and that characteristic is that there are more of those types of stars in the universe than any other kind.
Mm.
Okay. And that means
Huh.
that when you look at planets around other stars, there's more planets around those kinds of stars than any other kind. Now, when we look at planets in general, only from about the A down to the M there do they exist. So you start at A and then move down, and that's kind of where we could have planets that could potentially be habitable worlds.
Okay, cool.
Yeah. So this is how we classify stars: O, B, A, F, G, K, M. All right, like you see there. And the funny thing is, when I was getting my degree, they used this metaphor and said, if you want to, you can remember by saying, "Oh, be a fine girl, kiss me." And back then, it was okay. And then the female astronomers would say, "Oh, be a fine guy, kiss me." Is that was how we talked about it. Not fully, obviously. Once you get into the science, you don't even remember that. But when you're first learning, that's what ends up coming out. Okay, so this was this diagram is called the Hertzsprung-Russell diagram. Now, Hertzsprung and Russell, okay, Ejnar Hertzsprung and Henry Norris Russell discovered this link between stars that are fusing hydrogen into helium normally.
Mm-hmm.
All right. And the fact that when you plot them by brightness versus temperature, all those types of stars are on that little snaky line down the middle.
That's
And
amazing.
then,
Mhm.
yeah, and so we call this the HR or Hertzsprung-Russell diagram. Now, you notice the stars at the top. You see Betelgeuse up there, Antares, Aldebaran, and, all kinds of other stars. Pollux up there, which is in Gemini. Okay. You have Deneb and Rigel on the upper left in the blue. Okay. So, what are those? Well, after they stop fusing hydrogen into helium, when they run out of that fuel, they migrate off this diagram. And now there's tracks they take. They're really complicated tracks, but they start making other elements. They fuse other elements.
Mhm.
Okay, and one of the things that we hate to bring up and hate to look at is this diagram. Okay, this is our periodic table of the elements, right?
Memorize it.
Yeah, right. A little secret I have.
You can probably sing it, I bet.
You know I can. There's hydrogen and helium and lithium, beryllium, boron, carbon everywhere, and nitrogen all through the air, oxygen so you can breathe, and fluorine for your pretty teeth, etc. And all the way to the end, all the way to 118, which is actually the number Agnassen. So that said, these elements were created in the hearts of stars. Everything you see here was created in the heart of a star.
Amazing.
I know, isn't it?
Mm-hmm.
Yeah. And we have a diagram that actually shows which elements were created in the hearts of stars. There's another periodic table.
Oh,
and
cool.
if you look at the label, it says, okay, when the Big Bang occurred, the ones in blue occurred. Well, that's hydrogen and helium. Okay. And then when stars like the sun are dying, they swell into red giants and they will create the stuff in green, in various amounts. And exploding massive stars create some. And then you have white dwarfs that collide with each other or undergo a supernova. And those create the ones in the gray, okay, the elements in the gray. And it's funny because we found that gold, for instance,
Mhm.
okay, and gold is interesting, okay, because gold is one of those elements that's very valuable to humans, okay.
Yes.
Well, gold is actually an element that is only created with merging neutron stars,
Huh.
So when we talk about that, it's fascinating because, and I think that when you consider that everybody loves their gold, right? You go down to 79 there in the periodic table, then notice it's almost all purple. That means that most of the gold was created by neutron stars merging together in cataclysmic detonations and mergers. That's pretty cool. And look at all the other purple ones. So those other purple ones were also created by these merging neutron stars.
Wow.
So it's fascinating to think about how this stuff all works, Now, that said, I don't know if you have any questions. There's not going to be a test, Tara, on this, I promise.
Well, so they're all exploding and all those little teeny tiny elements are just out there and eventually they coalesce into a planet. I mean, is that how it all gets?
Yes, that's right.
Pretty
That's
much.
right.
I mean, that's amazing.
I mean, if we look at a star, this is
Universe.
this is a large star, okay, a massive star. They actually have all these shells around the core or in the core of burning material. Like when they told you they make other elements, well, you have iron is the highest it can go. Iron's number 26 in the table. But wait, Mark, there's 118, right? But supernovae, neutron star mergers, and other types of cataclysmic events create all the rest of those. Okay, but you could start with hydrogen fusing into helium, then helium fuses into carbon, and carbon goes into nitrogen and then oxygen. okay, and some of the other elements, and then beyond. And so now you look at the outside of this core of a large star, and you'll notice that we've got all kinds of different shells that are fusing the available fuel at that location,
Mm.
right? And this entire core is only about the size of the Earth, two times the Earth in size overall. Okay, and that's for a pretty big star. Okay, so we're talking about real small size cores. That's the only place where this nuclear fusion is taking place. So in this sun right here that we're seeing,
Mm-hmm.
15% of that circle is the core. All the rest is along for the ride. Isn't that wild?
It is. It's amazing.
Yeah. And so what's in that outside envelope is all the stuff that was made when the star was made. It was actually not made with, but the star was made with that stuff. Okay. So we look at this star and we say, wow, it's got all this potassium and calcium and magnesium and all that stuff. Is the star making those elements? No. Those elements were made in a larger star somewhere else. And that star went supernova, littered the cosmos with all this debris, and that debris floated toward us. And next thing you know, we had our sun made out of the hydrogen gas that was always there, the most prevalent and common element in the whole universe.
Mm.
And then that hydrogen made the star, and the envelope of the star, the other stuff that was accreted with it or contracted gravitationally to surround it, ended up being the stuff that was already made by another star. So the envelope is full of stuff made elsewhere. So only the core makes new elements in a star, not the outside. This is just stuff along for the ride we're looking at right here. That's just along for the ride. Pretty cool.
So are all those layers of cores, do they really look like that in layers, or is it all mixed together? Or is it different temperatures as you come out, or why is it different?
That's a very good question. See, they're layered like an onion, and the reason they are is because as you get closer and closer to the center, the pressure increases. Okay, as the pressure increases, other types of fusion can occur. So there might be a transition zone, between one to the other, but it's fairly well defined because a certain temperature is required to make hydrogen into helium, and that's around 15 million Celsius. Okay, and to make helium into carbon, you need 100 million Celsius.
Mhm.
Okay, so if the core begins to collapse after it runs out of hydrogen, it's going to get hotter and hotter and hotter, and then finally helium in there is going to start fusing into carbon, but it won't happen farther out because the temperature is too low and the pressure is too low. You have to have a certain pressure and temperature, so it won't be a very sharp division. It'll be a transition. It'll be all kind of mixed, but not one to like two shells up and down. It'll be soft boundaries on each of the shells.
Okay, interesting.
See?
So we're only seeing the outer shell of the sun right there. And
we're seeing the outer envelope, and we're not even seeing where the fusion's taking place. We've never seen that at all.
But even the huge, you can see on the picture there all the eruptions and stuff. That's all just from that outer shell, right?
That's correct. The outer envelope, yeah.
Mm-hmm.
Yeah. Now, the influence of what's going on inside can affect what happens on that outer shell for sure.
Yeah.
But you see those red things around the outside edge, those are prominences. That snaky black line, that's a prominence, just like on the edge, but it's coming towards you. And as it comes towards you, it cools off a little, so it looks dark on the photograph. Yeah. Really cool.
It is.
So anyway, 8 minutes ago, all this happened on the sun. And then suddenly that image is gone and the light is still coming in and you're seeing the sun as it was always 8 minutes ago, right? So there's our local area in the solar system, right? So on Earth at the time, you were probably just starting this conversation and finishing a quick snack, eating a candy bar and talking to someone saying, hey, how was your day? And you wouldn't know for 8 minutes if something happened to the sun. Okay. So that's pretty, you can see that. And that's the sun that you see in the sky every day, as it was always 8 minutes earlier. Now, let's jump out to Pluto.
Okay. Brr.
Yeah. Pluto is 5 hours away by light speed. Okay.
Wow.
And that's like 3.3 something billion miles. away from us, and that was 5 hours earlier. So whatever you were doing 5 hours ago, that's when the light from Pluto that we see tonight, if we image Pluto, this is not our image, obviously. That's when the light left Pluto to go all the way through the solar system to here. Now we can't travel light speed in our rockets at all. So we took over 10 years to get to Pluto. To get this picture took 10 years of travel through space.
It was worth it.
It was, because we see Sputnik Planitia there, the heart-shaped thing on the right that's white. Okay.
Oh, okay. Yeah.
Yeah. And we learned some really cool things. We learned that
Right.
Pluto's extremely dynamic. We learned that Pluto has an atmosphere. It's oxygen as well, but it's an extremely thin oxygen atmosphere. And we learned that Pluto has craters like on other planets, and we learned that Pluto doesn't have any craters in certain areas, meaning that Pluto has resurfaced itself. It's dynamic, has volcanoes. And what they are cryovolcanoes. They're very, very cold materials spewing out onto the surface, spilling out and covering in craters that may have formed.
Wow.
You know? So Pluto is very dynamic, and Pluto has a moon. Can you see that brown stuff at the lower left?
Yes.
Yeah, that material is also at the poles of Pluto, I should say, at the point where Charon is, Pluto's biggest moon. Pluto has many moons. Okay, I think it's 5 moons. I think Pluto has, and Charon, Charon, is opposite Pluto's reddish area that you see there. So it's out there. It's out there somewhere, you know.
Okay.
And that problem is that Pluto and Charon are tidally locked. They circle each other like this. They face each other. So you never see a different face of Pluto from Charon, and you never see a different face of Charon from Pluto.
Just like our moon.
Just like exactly like our moon for exactly the same reasons. It's so close that the differential gravitational pull has made it so that the Pluto's moon cannot rotate. It actually ends up rotating into a stable position, and then they end up tidally locked, as they say. Okay, so but that was 5 hours earlier. And by the way, Pluto's a planet. I believe that. I've said that. You know, in SkyTour LiveStream, we talk about this sometimes. I also say that, you know, we have a T-shirt that has a SkyTour LiveStream logo on it, and on the back it says "I need my space," and it has all the planets in there, including this one. There, because Pluto's a planet, so I have Pluto in there, and it's actually this image that's on the T-shirt. Okay, so it's a number of them around. It's a really, really cool, and some of the people in chat have actually bought some of these T-shirts. It's hilarious.
It's right there over my shoulder.
I think you have it, right? Oh, there it is. Yeah, right in the back. There it is. Excellent. Well, excellent. Yes, because Tara has one too. She's special.
Yes.
Yeah. So that's 5 hours ago. Now, Voyager 1 and 2 have left our solar system. Now, the distance is really incredible. It's now Pluto, 3.8 billion miles away. You basically literally almost double that, triple that, 2.5 times, and you get to where the Voyagers are now. And that was 23 hours ago.
Wow. It seems like it would take longer, because that's been going for a long time.
30 years.
Oh my gosh. I remember when that went out.
30 years. But in that time, it takes light 23 hours to get here, right, at that distance. So whatever was happening, you know, here on Earth, well, that was yesterday. You know, it's nearly a day later that the light arrives. So whatever you were doing 23 hours ago, that's when the light from the Voyager spacecraft reaches our deep space network. Okay, it was literally that long.
Wow.
You know, so now if you went, this is a cool thing. If you went at 60 miles an hour and you said, I'm going to go out to where Voyager is right now, and you went 60 miles an hour, it would take you 28,000 years to get there.
Oh my God.
Right.
Bring some patience.
I know. So you kind of get the idea, you know. Now the next leap takes us to the nearest star, Proxima Centauri. Now we see Proxima as it was 4.2 years ago. This is an artist rendering of Proxima Centauri. one of the problems with those deep red stars that I told you about, okay, those stars that are like
Like an
down in
M
that red
stars?
end of that, yeah, the M stars down the red end of that spectrum.
Mhm.
Okay, one of the problems is they also are very active and they have lots of flares. So this artist rendering is accurate. It shows lots of flares going on the star's surface, sending out all kinds of material. Might be X-rays and so forth. We got to be careful because that could be sterilizing. The ultraviolet radiation could sterilize potential for life that's trying to
Whoops.
burgeon
Yeah.
on a planet on that around the star. However, they do calm down. The nice thing about these particular stars is that the way they operate, the way they fuse hydrogen into helium, is like they're like little percolators. The very,
Mhm.
very first M star ever created in the universe, 13.8 billion years ago, is still going strong. They don't die in any reasonable time. They die
Mhm.
at about 1 trillion years in. So they have 1 trillion
Wow.
years worth of fuel in them. So they're like a forever source. So as they age and they change, they become different. They might lose some of the flaring that could remove life, but then they give the planets around them plenty of time to develop something. So that's something that I think is very important to understand too. That these planets are real, or these stars are very cool. There might be about the eighth mass of the sun, and maybe, and they have to be about um, 50 times larger than Jupiter. You know,
Mm.
to more massive, I should say. The best comparison to talk about these stars and their planets is to talk about Jupiter and its moons. Okay. Now they're very small. They could be anywhere from 1/10 to 100th the mass of our sun. All right. And there is one M star that's been found that's actually smaller than Jupiter, which is odd because Jupiter is the biggest planet in our solar system and
Mhm.
it's dwarfed by our sun. So there's an M star out there that's a
Yeah.
little bit smaller than Jupiter somehow, and it still
Wow.
existed because it's a compact object with lots of mass. I just think it's cool. So now we would go back 4.2 years and say, okay, well, on Earth, the year was 2021, and we were just finishing up
Wow.
dealing with COVID when the light we see tonight from Proxima Centauri started its journey. The COVID
Wow.
19 pandemic was starting, and the James Webb Space Telescope was actually still preparing for its Christmas Day launch. How about that?
That's amazing.
And that's when the light that we see today from Proxima Centauri left. Kind of neat. Now we go out 8.6 light years to the star Sirius, the brightest star in the sky. Okay. Sirius is out now. If it's clear out, you can go look at it. It's to the left
Mhm.
of Orion. Very, very bright star. It's it's the brightest star in the sky other than our sun, as I mentioned there, and it's an A-type star. Remember, in our diagram of the color temperatures, you see in the bottom there OBA. Yeah,
Mhm.
A star is what Sirius is. So a little bit of mass to it and a little bit of higher temperatures because the color is more of a bluish white. Okay. And so Sirius is very hot. And is it possible there could be planets there? Yeah, but only if the star is really stable and the planet's really kind of far away from the star. It has to be very, very stable star. And many of them are, you know. But so on Earth it was 2017 and Despacito was the song of the summer, okay? And that was the year we had that big solar eclipse which crossed over the entire
Oh,
United States.
yes,
Remember
that's
that?
right. That was so cool.
Yeah, yeah.
Yep.
And that was the first
Mhm.
time in a century that that occurred. Remember, Tara?
Amazing,
Yeah,
yes.
yeah.
I
Well,
made my little viewer out of a Cheerio box,
oh,
yes.
yeah, yeah, that's right,
Mhm.
that's right, so you could see the shadow,
Yes.
pinhole thing.
Yes,
Yeah,
yes.
yeah, yeah, no, that was great, and that was in 2017. So
Mhm.
think about that, that's pretty cool, you know? Now, then we go jumping out to another star called Altair, and we're gonna get to even more interesting objects too.
Cool.
Altair's neat because Altair was 16.7 years ago. That's 16.7 light years. Now Altair's out now as well, and the star, it's actually not quite. It's still on the horizon. It's rising. Okay.
Okay.
Yeah, and the star is going to be part of the summer triangle. Okay, the first star that we'll see is Deneb, the brightest star in the Northern Cross. We'll be visiting that later, and then Vega. We'll be visiting that later, and then we'll have Altair. Those are the three bright stars in the summer sky, and they form a triangle between them. We have Deneb, Vega, Altair, and that summer triangle is what people use to locate Cygnus the swan, Vega the lyre, the harp, and Altair the eagle. Okay, and Altair is a A-type star as well, and it's an A7 within each of those classifications of O, B, A, F, G, K, M, etc. You have a 0, 1, 2, 3, all the way to 9, and this is an A7 star. All right. Now, at the time the light left there, it was the year 2009.
Oh,
What were you doing in 2009, Tara?
have no clue.
Well, the iPhone 3GS was the biggest thing there was at the time.
iPhone 3.
Yeah, yeah. And as you can see there, people learned that the word unfriend meant something for the first time in history. It ended in the Oxford American Dictionary. And then Satoshi Nakamoto actually mined the first Bitcoin block back then.
Wow.
In 2009. So when the light that we see tonight from Altair left, Satoshi was just mining the first Bitcoin. I think that's pretty cool.
It's interesting. Yeah.
Yep. And Sully Sullenberger was landing in the Hudson on Cactus 1549, and he successfully made it, and everybody survived, if you recall, when both engines flamed out. And that was also when Michael Jackson died back in 2009.
Wow.
So when the light left Altair, these are all the things that were happening on its journey at the time it left. So pretty cool. Now we go to Vega, another star in the summer triangle, 25 light years away, part of the summer triangle. Okay, including, as I said, Deneb and Altair. And it's also an A-type star, but it's an A0, meaning it's the quintessential A-type star. Now, when we look at the spectra of these stars, they have lines in them. Okay, and one of the things that we look at is, that's the wrong thing.
Pretty.
Yeah. When we look at a spectrum, okay, we see the colors in the spectrum: red, orange, yellow, green, blue, indigo, and violet. Okay, but when we look at a spectrum from a star, we'll see dark lines in that spectrum too. And all the stars will have all those colors. Red stars, not so much blue. Blue stars, not so much red. But they'll have a semblance of those. But they have these vertical lines, and we call those absorption lines. That's because, if you remember when I talked about the sun, it's made with all those other all that other material in it, and those materials are part of the periodic table, and they all have different characteristics. So when the hot core material, the hot core heat is coming out, believe it or not, that envelope around the star is way cooler. And whenever you have a cooler gas with a hotter gas inside of it, that cooler gas can be excited enough to absorb some of the energy coming from the core. And it absorbs, and what looks like in the spectrum is a dark line. And every single element has a very specific set of dark lines. Okay. And this star shows the hydrogen Balmer series. There can be many different series from an element. And hydrogen shows these dark lines. And the A0 star, that Vega is right here, right, shows the most solid and I should say visible hydrogen lines of any other star. After that, they kind of they taper off, and before that, sometimes they broaden. But this is the quintessential star that we use when we do spectra calibration, because it's a great star to calibrate our spectra on.
Cool.
Interesting kind of thing. Yeah.
It is cool.
And Vega was our Polaris at one time. It was our pole star. Now, when? Well, that was 14,000 BC. And why did it change? And what's happening? Well, some people know that our Earth is like a top. It's sort of spinning like this, and it's wobbling. Okay. Well, where it's pointing, okay, changes, and that make us like a circle in the sky. And at one point, Vega was in that circle. Now we're over at Polaris
Mhm.
in Ursa Minor, the little bear, and we'll be back to Vega again. Okay, in about 12,000 years. It's a very slow
I'll read
wobble.
about it. Yeah.
It's a very slow wobble.
Mhm.
But when the light left Vega, it was 2001, and we were
Wow.
figuring out what was going to happen in the new millennium. The first Apple iPod came out, and the September 11 tax occurred
Wow.
in 2001, 25 years in the
That's
past.
true.
And then Wikipedia first showed up. So that's kind of interesting. And when the light we see from Vega tonight left, these are all the things that were happening here on the Earth at that time.
Mm.
So
Uh,
really kind of cool.
Yeah,
Go
I have a
ahead.
question.
Yeah.
So we're seeing the photons of light. Is that
Yes.
right?
Yep.
Okay, so are the photons that we're seeing today the same photon that left that image that was reflected all those years ago?
Yes, and that's right. And that's interesting the way you say that. I'll tell you why. In some of the more massive stars, when they go supernova, they're so far away, we won't see it for years because the light with that information is still going through space to get to us. Okay. And by
Right.
the time that end point comes to us, then the explosion comes. And we have to think about it that way because the universe is, we're always seeing it as it was, no matter wherever we look, we're always seeing it as it was, not as it is. And that's very true. That's a very good observation.
That's
You know?
interesting. It seems like with all the stuff in space, even though it's vast, it would change whatever was coming at us. So it's amazing.
Yeah, but once the light's emitted, the only thing that can change it is passage through some type of other gas or dust.
Mhm.
But it's not going to change it into different light than it was, really. So
Okay.
we will see that
Amazing.
light, just like with every star we see in the night sky. Yeah.
Very
So
cool.
this is the Eye of the Bull, Aldebaran.
Okay.
It's 65 light years away. So we see it 65 years ago. You know, and it's a giant star in that OBAFGK spectral class rating. Okay, it's called a K53. Now, why a 3? Well, because if we come back to this, okay, on the left side, okay, remember that snaky line is called the main sequence right there. All right, and so I'm going the wrong way. That snaky line is the main sequence, but we also have stars above the main sequence and below.
Mhm. Right.
Well, the thing is, once they stop fusing hydrogen into helium, they leave that main sequence. Now, we label the stars on the main sequence dwarfs, and they're designated by a Roman numeral 5, which is a V. So our sun is a G25, G2V, basically. Okay. But this star, okay, Aldebaran, is a K3 star. That is Roman numeral 3. And we're now in the realm of the giants. And up there just to the upper right on the chart, you can see Aldebaran in one of the 3 red stars up there. So Aldebaran has stopped fusing hydrogen into helium and is now migrated off that main sequence snaky line and is swelling now into a red giant star. So it's a K5 with a Roman numeral 3. Now, the K5 is the spectral class. The Roman numeral 3 is what's called the luminosity class.
Hmm.
The bigger the star is, the brighter its intrinsic brightness. So we call it a luminosity or luminousness. Okay. Yeah.
Luminousness.
Luminousness. Yeah. So this is a K5 Roman numeral 3. So it's a giant. It's a really, really interesting. Now, because it's redder, it's cooler than the sun, but it's much bigger than the sun. So why is it cooler? Because the energy generation is going on in the core of the star. And as that outer envelope of the star expands outward due to stellar evolution of a star that's run out of hydrogen, that temperature reduces because this stuff out here is farther from that energy generating core. If it was close, the star would be hot and in a different color, maybe blue or white. But as it gets further away, it cools off and turns redder. And so Aldebaran is an orangey star. So it's starting to swell. Its temperature on the outside is less than the sun, which is 10,000 Fahrenheit. Our sun is.
Ooh.
So Aldebaran is less than that. Okay, it might be about 7,000 or 8,000 Fahrenheit. I don't know for sure. But it's literally 44 times the diameter of the sun, and that is crazy to think.
Huge.
Right. Yeah, But because it's bloated, it's only 1.16 times its mass. So it was a star that was, kind of like the mass of the sun, just a slight bit more. All right. So it looked like a star like the sun. It looked like maybe an F-type star, right? Because the values change as the star evolves. If you start life as a G25 star like our sun,
right,
you're eventually going to end up as an M1, 1A or M13, a giant M1 Roman numeral 3, or something like that, because you are determined by your temperature, which is the color, and your luminosity. And as the sun expands into a red giant, when it runs out of hydrogen, it too will become an M-type star. It's off the main sequence up there in the upper right, where the other stars are, like the giant stars.
right.
Yeah.
That's great.
So it kind of shows how much it expanded, right? Yeah.
It would have fried up all the planets that were in that distance too, right?
I know it.
Well, I think it's time for a break, Mark.
I do believe you're right.
Yes.
We'll be right back, folks, with more of SkyTour Radio here on the UnXplained Network. We'll be back.
The conversation around UFOs has never been more serious or more complicated. On Saturday, March the 28th, from noon to 5 p.m. Eastern, the UnXplained Network presents UFO Audit, a digital conference taking a hard look at the current state of the UFO movement, featuring Micah Hanks, John Burroughs, Chiago Tchetti, and David Marler. 4 respected voices. No hype. Just real analysis. This is a free virtual event, so come be a part of the discussion and register now at the UnXplainedNetwork.com. That's the UnXplainedNetwork.com. The paranormal field is changing, and now, more than ever, it's time for professionals to lead the way. Join the Oz Professional Paranormal Investigators Association, a global network of serious investigators dedicated to raising the standard of real paranormal research. Access professional certifications, advanced training, and courses exploring true investigation, psychic phenomena. If you're a real paranormal investigator, be a part of the group defining the future. Join today. Visit ozinstitute.org. That's ozinstitute.org. The new book, How to Research a Haunted House by paranormal investigator Margie Kay and professional researcher Violet Wisdom is now available from UnX Media. This one-of-a-kind book explains how to do research on a house with uncommon methods and resources used by historic home researchers, and how to determine who may be doing the haunting and why. How to Research a Haunted House can be used by homeowners, renters, investors, and it should be in the library of all professional paranormal investigators. Get this unique book at unxmedia.com or amazon.com. That's unxmedia.com or amazon.com.
We're back.
That was fast. I was just rocking out. So
That's cool. I was like,
Yeah.
Oh yeah. I want to thank our producer Bill for doing that for us. He had the he edited our intro and did a nice job. Thank you, Bill.
Thanks,
Thank you.
thanks, Bill. You're
Bill's the
awesome.
man. He's hiding in the background. He's here.
He's awesome.
Yeah. So when we look in that Aldebaran's pretty cool. Now, 65 years ago, what was going on here when the light we see tonight from Aldebaran was coming to us? What did we see? Okay. It was 1961. And Yuri Gagarin was the first human in space.
Way to go. Yeah.
Kennedy was the first, was elected actually as the 35th president. We had a boiling point with our tensions with Russia, Soviet Union actually, and the Berlin Wall was made when the light that we see from Aldebaran left. All right, the Bay of Pigs invasion launched by the CIA failed. The Tsar Bomba was exploded, and it was of course the most powerful nuclear weapon at 50 megatons. Right, so these are the kind of things that were going on here. When the light we see that has been coursing through space for 65 years left Aldebaran. If you could go to Aldebaran and look back at Earth, that's what you would have seen happening on Earth at the time.
Very cool.
Yeah, really neat. Now, Regulus is 79 years ago in time. It's 79 light years away. It's a subgiant. It's one of those stars. It's a B8, so it's B8. And then 4, which is meaning it's on its way to becoming a potential giant star. Okay, but it's a subgiant. So this particular star is not on the main sequence anymore. It finished fusing hydrogen into helium, and it's pretty big right now. Okay, and it is in the constellation of Leo, of the Lion, right? And there's a lot of galaxies in Leo that we look at with SkyTour.
Nice.
Yeah, and so pretty cool stuff. Now, it was 1947 when the light we see tonight from this star left, right? And the Cold War term was first coined, and I think that was pretty cool. It was in July of that year that the rumored Roswell crash actually occurred, right?
That's what they say.
Arnold saw the flying discs in the sky, right? They look like saucers. And the sound barrier was sound barrier was broken by Chuck Yeager for the first time. And of course, the transistor was invented.
Oh, cool.
When the light we see from Regulus tonight left Regulus.
That's amazing.
So, and these are close by things, really close by. The
Hi,
Pleiades.
Marianne.
Is Marianne here with us?
I think so. Yes.
Where is she? I didn't see. Oh, yes. There she is. Yeah. Marianne Robb is here. Marianne is
awesome.
One of the people that she's the third part of our SkyTour LiveStream organization. And she's very supportive of us, does more than she should.
That's right.
And she'll tell you so. No, I'm just kidding. She's sweet. She's good. So the Pleiades, the seven sisters, we see in the winter, right? They're out now. When you
They're
look up, you
pretty.
see,
Mhm.
yeah, they're up in the sky. You can find them with an app on your iPhone or your Android system, and you'll notice you can count about 4 to 5 stars with your eye. A pair of binoculars, you'll see a lot more. Okay, but it's very famous for those stars. Now you got Atlas, Pleione, Tegeta, Alcyone, Maya, Merope, and Electra. However, there's actually over 1,000 members of the Pleiades star cluster. See all the,
Wow.
I know. And you don't just have the seven sisters; they brought all their friends.
They did. Boy,
They brought
word
all
got
their
out. Party at the
oh,
Pleiades.
that's right. That's so very funny. Party at the Pleiades, everybody. That's right. So they're all here. And the nice thing is, when you look at this photo, which we took with the SkyTour telescopes, you see in that photo, you see dust clouds around the stars.
Right.
That's illuminated dust that's illuminated by the B-type stars, the B as an OBAF, the B-type stars that make the primary Pleiades stars. The entire cluster is moving through a dust cloud. Now, when they do a motion analysis of which way the stars are moving, because they do move, and we calculate a quantity called the proper motion of stars to
Okay.
figure out how fast they're moving per year. It's negligible on a yearly basis, but it's actually moving quite fast, but not being so far away. 447 years ago, 447 light years, we don't actually see that movement for many, many years.
Mm-mm.
But if you also calculate and look at the direction that the dust is moving, you'll see that one's going one way, one's going the other. So it shows us that the
Oh,
star cluster is just passing through a dust cloud, and that the dust cloud is not part of the star cluster. Interestingly, it's just happens to be in the dust cloud now. Now, another interesting thing is that here on our Earth, we're, like I said, all these light years away, 447 light years away. Here on Earth, we notice that we might actually be in the same dust as the Pleiades. Now, this is ongoing research. We don't know the full answer yet.
wow.
Yeah. So if you look at a galaxy picture, you see a galaxy has all these dark dust lanes, and they go on for, thousands of light years within a galaxy, right? And those dust lanes might be something that the Pleiades is passing through, and the dust lane is moving. And it's possible we've been looking out through the same dust lane as the Pleiades are immersed in right now. And that's new research that's going to actually shake up a few things we understand about the universe.
Interesting. So
Yeah.
that's different than the dust that's in the spiral arms or the spiral arms that we're looking through.
It could be part of the same dust from another spiral arm, because galaxies have more than one spiral arm typically.
Right.
When we look towards Sagittarius in the summer, we have that big bulge of stars. That's looking toward the center of our galaxy. When we look at the Pleiades and Orion, we're now turning away from the bulge over here and looking out there somewhere at another spiral arm, because we're inside the galaxy. So we're like, just less than 2/3 of the way out, just over a third. And so when we look one direction, we're seeing the outer arms to us, and we look in the other direction, we're looking towards Sagittarius in the center of the galaxy.
Right.
So we look in all directions, we're seeing the entire galaxy expanse around us. Okay. So as it turns out, some of this dust could be from one of those outer spiral arms, and we could be in it. It's really cool. Yeah.
And like you've taught us before, it's the universe is so huge you don't realize you're in it because you don't really see it, right?
Exactly right. Exactly right.
It's weird.
Yeah.
You'd think you
So
could make it easier.
we love looking at the Pleiades, and when we see the light from the Pleiades, none of us actually think about the fact that it was 1582 when the light you're seeing tonight left those Pleiades. And the Gregorian calendar was fixed to prevent the seasons from drifting into different months that we didn't expect.
Okay.
And so, and that fix back in 1582 was that on October 4th, people went to sleep, and when they woke up, it was October 15th. So they lost 11 days to fix the Gregorian calendar.
So really, it was just the next morning, right? They didn't
That is
sleep for
correct.
14 days. Okay.
That is
I'm
correct.
like, how did they do that?
Yeah, but this is a fact that barely anybody knows.
Yes, I've never
That's
heard
pretty
that.
cool. Yeah.
Uh-huh.
You know, so that said, the Pleiades are interesting. We look at them, we don't even realize that we're seeing light that left when the Gregorian calendar was fixed, or when people had to, go to sleep one night and wake up 11 days later, and not even realize it. And of course, it was because of the fix process. So they
It's
lost 11 days. I mean, it's pretty
like
cool.
daylight savings time, right?
Yeah, it's big time.
On a large scale.
Yeah. Now, Antares, the eye of the scorpion, in the Scorpius the scorpion, is in the summer sky. It's 550 years in the distance in time, 550 light years away. Now, this is an M-type supergiant, okay? And that means that it's going to be an extremely bright star because it's got a massive size, diameter. And when we look at our Hertzsprung-Russell diagram, you can see Antares is up there in the upper right of the diagram, and only bigger than his Betelgeuse. And Antares is a massive star, and it's one of these type 1A supergiants, meaning that it's so big that it will go supernova, guaranteed, and it's on its last legs. All right. Now, we took this photo. This is Antares in the center, and then to the upper right is a globular cluster.
That's cool.
Okay. Yeah. And those are called halo objects. We'll see those later as well.
It's like snowballs coming.
Yeah, right. They orbit the galaxy, though. They orbit the galaxy.
Okay.
And there's some new theories on what those might be we can talk about. But see, if you put Antares where the sun is, okay, its radius would take it all the way out to Jupiter's orbit.
Wow.
Okay, almost to Jupiter's orbit, past Mars, right? So into the asteroid belt, and not quite reaching Jupiter. So it would actually swallow Mercury, Venus, Earth, and Mars, and then a bunch of the asteroid belt. So this star, that's just the radius. Now it has a diameter to it. So you got to go all the way to the other side of the solar system, on the other side of the sun, and finish the sphere. So that's how big this thing is. Okay. And it's so big that the outer regions of the star are cooler, cool enough, in fact, so that molecules can form out there. Now, in the envelope of the sun, for instance, it's all what we call plasma. There's no atoms in the envelope of the sun. It's actually just protons, okay, like the atomic nuclei with free electrons roaming around. And it's too hot for the electrons to rejoin the protons, because the electrons can't actually get back into the atom because they have too much energy. They're too excited to be free. We're
free.
We're free. Not going back. Yeah,
Run
exactly.
away.
Exactly. So this dust that's formed out there is the stuff that ends up making the spiral arms that we see, in terms of the dusty dust we see in the spiral arms. Yeah. Okay. In fact, in this photograph, just to the right of Antares and down to the lower right there, and up a little bit just below the globular cluster, you see that dark area? That's not a void in the stars. That's dust that's obscuring the stars behind it. And that was made from other stars that have littered the cosmos, both with their supernova debris and with their outer atmosphere dust production. So that's where it comes from. And because we have so much of it, a lot of that has happened in our galaxy.
Wow.
So
and there's gold in that there dust, right?
And yes, as a matter of fact, there's probably gold in that dust as well, because when you make a planet, well, you get a certain proportion of that gold, don't you? All right. And all of that gold was created by merging neutron stars that collided and catastrophically collided. And those mergers create those elements. Remember this other diagram here. This is the diagram that shows us that the merging neutron stars up there in the purple, right? We see Au, gold, right? That was created by merging neutron stars.
79, yeah.
Yeah, and we get platinum that way, iridium, osmium, okay? And we've got plenty of other elements we get, polonium, right? So, this is the kind of thing that it took a long time to figure out with stars where all these elements come from.
Yeah.
There's just so many, but and Antares, now we're starting to get out there a little bit more. So what's next after Antares? Well, first, let's talk about what was happening here when the light we see tonight from Antares was arriving. Left, I mean. It was the late 1400s.
Oh my goodness.
Yeah, yeah. Leonardo da Vinci was 24 years old when the
Ah,
light we see tonight left Antares. Okay, Christopher Columbus was heading across the Atlantic. And Michelangelo, by the way, was an infant. He was basically, 1 year old, okay, in Italy. Michelangelo, when the light we see tonight left Antares. Isn't that crazy?
that's cool. Yeah.
Yeah, yeah.
I like the art theme you have going on here.
Oh, it's kind of cool, yeah.
Mhm.
The Aztecs were at the height of their power. The Incan Empire was expanding rapidly. Vlad the Impaler died.
Well, that's a good thing.
That
Yeah.
was a good thing, yeah. Okay. He should have been impaled.
And
What
say,
I
where did his head on a spike end up?
Yeah, right.
Mhm.
So that's what happened when Antares light we see tonight left the star.
That's
Okay.
cool.
Yeah. So now Betelgeuse. Betelgeuse is the crown jewel of Orion. It's the upper left star, the orange-red supergiant. It's a Type 1A supergiant. It's an M-type star, meaning it's red, meaning it's cool, but it's off the main sequence, as I've mentioned, and it's a supergiant. So it's still the temperature of the smaller red dwarfs, but it's a red giant, so it's an M-type, and it's not a luminosity class V, which is 5, like the small dwarfs that are Jupiter-sized, but it's a super-sized star. It's not the biggest star, incidentally. And so it's an M1A supergiant, the 1A indicating its size and type. So the luminosity class. So it's going to go supernova eventually, and its outer cool regions do like we talked about. It makes dust in the outer regions, and it sort of sloughs off the star. It actually gets so far out that if it's even pushed a little bit, it can just keep going. It's no longer gravitationally bound to the star.
Oh, okay.
Yeah. And this star here is much bigger than Antares in that regard. So if you put it where the sun is, it would actually reach Jupiter. I didn't say that here, but it would actually reach Jupiter. All right. And
Big.
Betelgeuse and Antares are two of the stars that we actually can image for real. We can actually see their disks. And the reason is because they're so massively large.
Oh,
And it's because of that luminosity class of the M1A, Roman numeral 1, little a. Okay. So those big giant supergiants are so big that we can use special techniques to image the stars themselves. And when we look at Betelgeuse, we see something really odd. Its surface has this really strange protrusions on it all over the place.
huh?
And I'm wondering if I I didn't do it. I was hoping I had included an image of the surface of Betelgeuse.
Oh, I'm intrigued.
Yeah. Well, Betelgeuse was a definite candidate for this because of its size. And so when they looked at it, they saw that it had all these bumps on it. It didn't look like a round sphere, kind of like the sun. It actually had this extensions off one side, extensions off another off the bottom, these gigantic lobes of material. Here's what's happening. Inside Betelgeuse, what's going on is that the star has convection zones like a pot that's heating up with water. And so massive bubbles of material come off the star and then split apart and fall back. So Betelgeuse, probably, if it didn't ever have life on it, and I'll tell you why. Because when Betelgeuse formed, I'll bring this diagram up, it was actually up there. It was a top left element on this diagram. It was a O-type star, very, very hot, very, very blue. And these stars only survive for a few million years. Then they explode. Then when Betelgeuse comes off, what ends up happening is that when Betelgeuse comes off, let me just get my focus back. Okay. It ends up that the star drifts backwards on this diagram. And it's a complex study of what are called tracks of evolutionary tracks of stars, but it ends up to the upper right. So it actually ends up getting larger and larger and losing its temperature, meaning it's going to drift down the chart that you see there from the O's to the B, A, F, G, K, M. However, it stays moving horizontally up there from the O-type star location at the top left into the top right, right? And so when it migrates that way, it ends up becoming a massive star that will go supernova. It's actually one of those stars that may already have gone supernova. It's 640 years in the past for us. So if it exploded 639.9 years ago, well, in just a short time, we should see it go supernova.
Ooh, I hope we get to see it.
I hope so too. I'd love to see that.
Oh, it'd be so cool. And we'd see it in the day, right?
Actually, in Betelgeuse's case, we'd even see it during the day.
Okay.
We would indeed. We would indeed. Yep. Yeah. So that said, when we look at Betelgeuse, we're seeing a planet that could literally engulf Mercury, Venus, Earth, Mars, and possibly Jupiter. And its light that left 640 years ago, back when it was the late 1400s. So now, no, I was wrong. I'm going ahead. I went into that. 640 years ago, it was 1384. And the Black Death had just finished ravaging Europe. And at this time, the Black Death. And it was at this time when the light we see from Betelgeuse tonight left that the Ming Dynasty was beginning its long rule in China. Just beginning. Isn't that crazy?
Mm-hmm.
So this is the perspective that we're talking about here. Now, let's go a little further. The Orion Nebula. And this is a very complex photograph, but the Orion Nebula is actually in this photo. It's down at the bottom. Okay. And at the top, you see a bluish nebula. And in the middle, you see this dark dust in there. Orion is part of a giant molecular cloud. It's called the OMCC, the Orion Molecular Cloud Complex. And so anytime we take photos in Orion, we'll see this brownish black dust all the time. And that's the stuff that stars like Betelgeuse create, both when they're creating dust in their outer atmospheres and when they go supernova. So the quantity of dust here shows that there have been many, many millions upon millions upon millions of previous supernovae explosions, right?
Wow.
Yeah. And the Orion Nebula is a stellar nursery, and there is a bright set of 4 hot stars, hot blue stars, right in the middle. The brightest part of the nebula down in the bottom there, it looks like a bright white area. That's where the trapezium is, which is those 4 stars.
Mm-hmm.
Yeah.
It looks so soft and billowy, this picture, such a contrast to what it really is, right?
Yeah, and it was 1,344 years in the past, which is 1,344 light years. Wow. And so if you got out, let's say you went out to that dark dust, you say, I want to go out to that pillow.
Okay, yes.
By the time you get within, say, 500 light years of it, you won't see it anymore.
Oh.
Because it's going to fill your whole view, and you're not going to see any of the actual features anymore because it's going to be filling your view. And then when you get out to it, you'll be in it.
Mm-hmm.
And it's not going to look much different. The stars might look a little bit redder when you look at them because dust like that tends to redden star color in the same way that the sun is red on the horizon when it rises and when it sets. Okay. So it's kind of neat. But the interesting thing about this is that you can actually see this nebula with your eye. And where is it? Well, most people know. If you look at the belt of Orion, the 3 stars, and you just drop down from the belt toward the bottom of Orion's squared off image, you'll see a fuzzy thing just below the belt. We call that Orion's sword. And inside that sword is everything you're seeing right here. That's what's actually there.
Is that the running man on top there?
In fact, it is the running man.
You can see him.
Yeah.
He's like, ah.
He's going, wait for me.
It's like a Bigfoot or something.
That's exactly right. Yeah. And so as Tara alludes, we name different objects in the sky, and so this became the Running Man. Okay, and it's got an actual designation, a new general catalog or an NGC number as well. The Orion Nebula down below is known as the Great Nebula in Orion, and it's also known as Messier 42. Okay, Charles Messier in the 1700s was cataloging objects in the sky to avoid, because they weren't comets, because he was a comet hunter. And this became something he cataloged as a non-comet object. Just ignore it.
Nothing to see here.
Yeah, can you ignore that? Oh my gosh, it's really beautiful. I agree.
It's gorgeous.
Yeah. So what was happening here? The year was 680 AD. The golden age of Islam had just begun to flourish. The Tang dynasty had reached the pinnacle of its influence at that time. So we're looking at history. When you look at the Orion Nebula tonight, that's what was happening when the light we see tonight left that location out in space. Isn't that something?
It's awesome.
It tells you the size of the universe in so many different ways. Now, Deneb, that third star in the summer triangle that I mentioned, is 2,600 light years away. It was 2,600 years ago when the light we see tonight left it. And you say, wow, that's pretty cool. Now, it's an A star, like we talked about, and it's a 1A supergiant, meaning, and you can see the 1A here, so you can get an idea what I meant by that. Roman numeral 1 with a little a.
Right.
Like Betelgeuse being a 1A, a luminosity class, Deneb is a 1A luminosity class. It's a supernova in waiting. Eventually, it's going to go supernova and litter the cosmos with an immense amount of incredible stuff, and that which will include all the elements that it made in its core being littered and beyond, right? But this is a very massive star, right? Because it's large, but it's still blue. Okay, I mean, it's still bluish white, and that's because it's massive but big, and this star will only live a few million years as well, right? Amazing to think that stars are the givers and takers of life, but they really are, And here on Earth, it was 570 BC. Pythagoras was alive when the light that we see tonight left Deneb. Isn't that crazy?
That is crazy. He was drawing squares and triangles.
Right. He was coming up with the Pythagorean theorem.
He was.
Yes. Right. So he was alive back then when the light we see tonight left there. And of course, it was also the Neo-Babylonian Empire's height at the time. So a fascinating view of this guy. And now, why would I put this one in there? Well, there's a reason. I'll tell you. This is 18 Scorpio, one of the stars in Scorpius, okay? It's 4,600 light years away, okay? Now, the reason is because it's a solar twin. Now, that means that this is a star that has the exact same composition as our sun. And that means it's one of the stars that formed with the sun in the same place.
Oh, cool.
Okay? And now it's 4,600 years in the past. It's 4,600 light years away because we've been here for 4.6 billion years. And in that time, the stars have migrated apart. Now, they're looking for more solar twins as well, by the way. We'd like to find more. Okay. Now, the mass, the temperature, and its chemical composition are nearly identical. So that's like fingerprints. It's a fingerprint of the solar nebula within which we formed. And so this star is a solar twin. Now, guess what? If it's a solar twin, does that mean that it could have planets?
Yes.
Yes, it does. It means maybe it does.
Is this still a silly question? Is this still in our galaxy, or is this outside of our galaxy?
No, it's 4,600 light years away, and our galaxy is 150,000 light years in size. Okay. So it's well within our galaxy. And so that is the interesting thing with this. Now, at that time, it was just about 2,500 BC, and the Great Pyramid at Cheops, or Khufu, was under construction when the light, when the light from this star left. okay, and was on its way here.
Wow.
Now, you got to understand, okay, the pyramids were ancient in history when King Tut was around. How about that? Think about that. Tutankhamun was 1,200 years after that.
Oh my goodness.
But people think King Tut pyramids. Yet he came 1,200 years later. And Cleopatra, 2,500 years after that. You know, and we've actually heard ad nauseum, you know, that they used lots of slaves to build the pyramids and all that. But in fact, it wasn't true. In fact, you wanted to be a pyramid builder because you got the best food, you got the best medical care. I'm not kidding. So you wanted to be, in fact, whole families just aspired to be pyramid builders. And so this was one of those things that was one of those trades at the time that was like the equivalent of those that build the large skyscrapers today. They're the elite of the elite. They're the ones that know what's going on. They have all the best engineers. That's what pyramid building was back then.
That's amazing.
Not slaves. Envied position.
That's
Crazy,
cool.
huh? Yeah.
Hey, Mark, on this particular star, that's our twin. So now we've gone around the center of the galaxy. What is it, 17 or 18 times, they say?
About 19 or 20 or so.
Okay. All right. So we've been separated because of that, right? So we don't know. I mean, is that why it's so far away from us? It's on its own path as well?
Yeah, every star has an orbit around the galaxy. We all orbit the galaxy. Every star does. But every star is also subject to the tug and pull of other stars. So if we formed in a cluster of several other stars like this one we see here, well, we were getting tugged and pulled too. So maybe we're far away because we were tugged away and the other one was tugged away. And so over time, those differential gravitational pulls are going to pull us in all kinds of directions. You know?
It's neat to think about.
Yeah.
Cool.
Yeah. So it's interesting. It's really interesting, you know. And I want to say hello to, let's see, we got Mallory's here. Hi, Mallory. How are you? And we have Adrian. Thank you. Greetings from Park Hampstead. Very, very close to me. Ronald asking, why is it blue and our sun is yellow? This star here, this is 18 Scorpii as photographed by a different telescope than ours. So it's the star is identical to ours. It's a G2 as well. Yeah. And Mr. Django from Belgium is here. He says, hi, Mark and Tara, all the beautiful people. That's great. And so things are cool. It's great to see you all here. And we'll just continue, or else if I say hi to everybody, I'll just run out of time, but I want to, you know. I was thinking of streaming tonight, but it doesn't look like it's going to be clear out there. So I'll make that determination after the show.
Sounds good.
Yeah. So 18 Scorpii is a solar twin. Okay. Cool. And now let's go out 5,200 years ago to the distance of 5,200 light years. And we see another image that we took of an object called the Rosette Nebula. Now, you'll notice that the Rosette Nebula, it looks like a donut, which has a hole in the middle and then a surrounding nebula. Well, first of all, why does the nebula glow? It's glowing because there's a bright cluster of stars that you can see right in the middle of that thing, okay? And they're hot and they're blue, and they're sending out a lot of ultraviolet radiation, which excites the atoms that are floating free out in this nebula. And as it excites those atoms, the electrons bounce off the atom in a term we call ionization, and then the atom's electrons out there will eventually lose some energy and fall back into the atom. And when they do fall back into the hydrogen atom, the predominant light that they give off is red, and that's this here. Okay, so that's why the hydrogen gas glows red most of the time. Okay, now the central opening that you see there, that central donut, well, the reason that happens is because of the fact that the stars are so hot, so young, they're pushing out with all of their stellar winds, and they're actually clearing a cavity around them. Isn't that crazy?
It is. It's, yeah, you don't think about it being windy.
Yeah, that's right. That's right. And a very, very good statement by Daisy and Zoe Amethyst. we are time travelers. We are. We're traveling through time, and everyone that looks at us sees us at a different time period as well, even aliens. So they see the oxygen in our atmosphere, and they may come here looking at that. But when they get here, they'll say, "Whoa, there's a lot more going on here than we thought." That's always going to be the case.
Yep.
Yeah. So I think that it's interesting to consider the stars in terms of time travel, because that'll help us when it comes time to look at potential alien life looking at us. What are they going to see? They're not going to see our civilization now.
The dinosaurs, maybe?
Yes, that's correct.
Okay.
If we go if they're looking at us from a galaxy far away, but we'll see that. Don't worry. So here on Earth, it was 3000 BC. So when the light left this object you're seeing right now,
Beautiful.
okay, yes, Stonehenge was just a ditch. It wasn't even built yet. Okay, it wouldn't be built for another 500 years. Right? And you folks can read that. You see what's going on. And it would be another 200 years before the final blue stones were put in place in Stonehenge.
Wow.
Because it took approximately 1,500 years to complete through generations of people. So that is just incredible. Now, 6,500 years in the past, 6,500 light years away, this is a supernova remnant. This is called the Crab Nebula. Now, this was seen by Chinese astronomers in 1054 AD.
Wow.
Now, the light traveled 6,500 years to get here for Chinese astronomers back in 1054 to see it. But at the time that it actually blew up, it was a lot earlier. So there's a central pulsar in here. And sometimes when a supernova occurs, the star is obliterated. And of course, that obliteration, that explosion in all directions, forces an immense amount of pressure into the core. And that makes it into this tiny, tiny neutron star. Now, a neutron star is literally this big compared to a city.
Wow.
Okay, and that's how big a neutron star is compared to a city. It's very small.
Huge.
Maybe but that's only about 25 miles across, maybe. So they're small, 25 to 30 miles across. A white dwarf, like in the heart of a nebula that like the sun would create when it dies, is about the size of the Earth, right?
Okay.
So you can see in the middle of this object that we took, you can see a star in there. Well, it looks like a star. Well, this is the pulsar, and they actually spin rapidly because all that energy, that angular momentum it's called, that's transferred to that core during the explosion, it's not even. And so the star can be set to spinning at very different rates. And they are like atomic clocks. That spin continues. It slows down ever so slowly, but it takes billions upon billions of years for them to start really slowing down seriously. So the Crab Nebula pulsar in the center, and we call it a pulsar because it has a hot spot that hits us, sort of, as it goes by, it's like, it sweeps by us like a lighthouse beacon. Okay, and we see the energy. It's actually spinning 33 times per second. Okay, meaning this object is moving 33 times per second, circular around in a circle. That's pretty crazy, but it's not the fastest. What's that?
It's heavy, right?
Very massive. Yeah. If you took a spoonful of that and tried to hold it on the Earth, it'd weigh billions of tons.
Oh my goodness.
A spoonful.
Wow.
Now, yeah. So think about this now. If you see stars spinning 33 times per second, you say that's pretty fast. It is, but guess what? It's not nearly the fastest. Not at all.
Wow.
The fastest pulsar is spinning over 715 times per second.
Wow. How can that be measured? Wow.
Yeah, they can measure it, okay, because they can see how they can break apart the rotation, and they can slow it down, and capture all the lighthouse beacons swinging by. So it's like, but it's almost like, it's like almost like a static. It's happening so fast. And so they can measure that frequency. And the star is so dense that it holds itself together with even a spin rate like that. That's what's cool about these stars. You know?
It is interesting.
Yeah. So back in time, it was actually 5500 BC when it actually exploded. Then it traveled 6500 years to get here, where Chinese and Arab astronomers saw it in 1054. Okay, so
Wow.
so when it actually happened, it was before the beginning of our written history, which is kind of cool. Now, that's neat to think about because it was Mesopotamia where this occurred, and if you remember, they would make little tiny marks in wet clay, a cuneiform language, right? And that was before that actually even happened or was invented. So the light we see tonight from that, okay, left before written language was even created on Earth. And we look at it and say, oh, wow, the Crab Nebula. Not even thinking of all the history that light has seen as it was winging its way toward us.
It's pretty neat.
Yeah. Now we're going back in time, remember? So at this point, Stonehenge wasn't even built. It wasn't even a ditch. And from this point, it wasn't going to be started for another 2,500 years.
Oh my gosh.
I know, right? Absolutely crazy.
Time flies.
Yeah. And then the pillars of creation popularized by the Hubble Space Telescope and our SkyTour LiveStream image here you see from our observatory. Yeah, it's 7,000 years in the past. We see it as it was 7,000 years ago. And it's a stellar nursery containing those famous pillars of creation, which you can see there, the vertical thing sticking up there. Okay, like it looks like fingers sticking up.
Right.
Okay. Yeah. And again, this is the building blocks of life are being formed inside the dark areas of this nebula because the dark areas contain a lot of these molecules that were left over by the stars' outer reaches, making them, and through supernovae that occurred. All right. And there's a whole reason why the pillars look like they do, and that's another topic, but it's called stellar erosion. They're eroding gas and dust because they're so powerful stellar winds. And you see the cluster there at the upper right of the picture.
Yeah.
And it's pushing dust and gas down, and only the densest parts survive. And so stuff behind that dense part will also survive. So you end up with a pillar, like a finger-looking thing.
I always thought they were pushing, like erupting up versus being eroded down.
Yeah, exactly. Yeah, that's actually a very good point. Yeah, they're being eroded down from those bright stars you see just to the upper right of them. Yep.
That's cool.
Yeah. Now, what was happening here? It was around 5,000 BC, and Mesopotamia was flourishing, and there were some pre-Sumerians, around. And it's interesting, too, that the agriculture was just starting when the light we see tonight left that. You know how we are with farms today and how advanced it is.
Oh, yeah.
Genetic modifications that we all hate. Okay. Not even a glimmer because it hadn't even begun yet. It was just beginning.
Wow.
And here's the thing, too. The Sahara Desert was lush and green.
Oh.
Yeah. See? And we had, at that time, we had just been coming out of an ice age, and it was very, very, it was getting warmer. And as we come out of the ice age, the land that was, exposed by the ice age was being flooded and then exposed routinely over the course of time. And so this is something that caused us to, move and migrate and learn new things. I mean, it also assisted with evolution over time, but it takes many hundreds of thousands of years for evolutionary changes to occur. But at the time, the North Star wasn't Polaris. The North Star was Thuban, which is in the constellation Draco. Remember I said the Earth wobbles?
Right.
And so the North Pole, as it wobbles, traces out a circle in the sky. And so it was Vega, okay, it comes around, then it was Thuban, right? And then it was Polaris, and it's going to go back to Vega eventually, right? In another just over 12,000 years.
Yeah.
So there's a lot going on. And so that's the Eagle Nebula, 7,000 years in the past. Okay. Omega Centauri now is the biggest globular cluster in existence. There's over 10 million stars in this cluster.
So dense.
It is.
Yes.
It is. And if you were inside of this, you would see stars everywhere you look, and they're probably all approximately, well, maybe not, but they would be approximately all the same brightness, which is kind of cool. Yeah. So your sky would look very different. However, globular clusters appear to be areas that filled with stars that were created back at the beginning of time, the beginning of the entire universe, roughly. So the stars in there don't have a lot of elements in them. Okay, like we see when we look at this table, there's a lot of elements. But these stars had only those blue ones, hydrogen and helium in them for the most part. There's a few trace additional elements in there, but they only had hydrogen and helium. So it means that they didn't form in an area where there was a lot of dust and debris that could be made into planets. Yeah.
So there. So never mind.
Okay then.
Oh my gosh. Well, I was just thinking, if that was created near the beginning of the universe, can we see all the light that has been created since the beginning of time? I mean, can we go back that far in time with an image?
I'd love to say we could, but this is 15,800 light years away.
Right.
So we're seeing it as it was that many years ago. But if we want to consider where the beginning of the universe was, if we looked out, the farthest we can see is the cosmic microwave background, which is the limit of what we can see right now. But that's not the limit of the size of the universe. That's how it was 13.4 or so billion years ago. But that took 13.4 years for that light to get here. So during that time, it expanded even more. So the universe is bigger than 13.4 billion light years, or 13.8. Its age is 13.8, okay? Because the farthest thing we can see is like around 13.4. The additional amount comes from the universe not having atoms yet, and so we couldn't really see anything. But yeah, so in that case, what happened is the universe kept expanding while that light was coming here from all that distance. But then we discovered that the universe isn't expanding at a constant rate, like Edwin P. Hubble said in the 20s, but at an accelerating rate of expansion, which meant, well, we've got a lot of things wrong here. So that means that the universe is bigger than we thought. So if it's accelerating outward, it means that the explosion is sort of still occurring and we're still moving outward and at an accelerated rate. And that means that over that 13.4 billion years that stuff was coming, it didn't just expand another 13.4 billion light years. It expanded a lot more. And when we double it and do an analysis, it comes out that the entire universe that we'll never see is over 92 billion light years in diameter.
Wow.
Yeah, 92 billion. Wow. And we can never see it all because the light could never possibly reach us. Yeah, isn't that crazy?
And it'll be, as time goes on, we'll see less and less light, correct?
Yeah, that's a matter of cosmology where they discuss the nature of the remainder of the universe and the end of time, so to speak. There'll be less stars. And now if the universe is expanding outward, though, as you say, and things are getting further from us, there will come a point where we won't see their light anymore. You know, luckily there's enough stuff nearby that's going to keep us interested for some period of time. You know.
Oh wow, that's cool.
Yeah. But here on our planet, it was 13,800 BC. The glaciers were retreating after the ice age. Another ice age was coming to an end, and the oceans were rising as the ice melted, of course. And there was a thing called the Great Thaw as we're coming out of the Ice Age, and land bridges connecting Alaska with Siberia and the UK to Europe were still dry, allowing migration to occur. Woolly mammoths and mastodons were still roaming. Saber-toothed tigers were still around, at that point. And that's what happened when the light we see tonight from Omega Centauri left that object. Isn't that crazy?
Cool. It's
all
cool.
that time it's been spent coming here. Now we have the Large Magellanic Cloud. This is a dwarf galaxy that is associated with us. It is known as a satellite galaxy, yeah, and it's got its own really interesting objects in it. Our galaxy has pretty much ripped it apart, but we still see a cohesive, shape to it, right? And as a galaxy like this, one of the things it may have is a supermassive black hole at its center as well, like we do. We have that famous 10-year study of our central black hole, and you see stars orbiting nothing, but they're going like this, zoom, zoom, zoom.
Oh, cool.
And over 10 years, we can see they're orbiting the central black hole. Absolutely crazy. And it's a SMBH, a supermassive black hole. Okay. Now, 160,000 years in the past, what was happening on Earth back then? 160,000 years ago. It was 158,000 BC. Okay. And this was when the modern human was actually just emerging from Africa. And we call them modern humans, but you know how they had different forms, right? Lucy was 4.2 million years ago, right? And so forth. So we had Homo habilis, we had Neanderthal, we had Cro-Magnon, not in that order. Okay. But it was interesting how this all came about. Now, the other thing too is the oldest fossils of our species, known as the Omo remains, okay, were found in Ethiopia, and they roughly date to 160,000 years ago. So when the light left that object right there, the earliest remains of our species were living in Africa.
Oh, that's cool.
Yeah. See, it gets crazier now. Now that we get out of like 1.3 seconds and 8 minutes, now we're seeing the whole universe. And this is just our galaxy.
Right.
Right? We're not even outside our galaxy yet. Big place.
That's amazing. That's amazing.
Now we are outside our galaxy. This is the Andromeda Galaxy, 2.5 million light years in the past, or 2 million years in the past, 2 million light years away. Okay. It's the closest big spiral to us, and it's actually heading right for us. We're on a collision course. In about 3 billion years, it'll pass sort of right through us. It might tear us apart because it has about 1 trillion stars to our low end estimate of 150 billion, high end estimate 400 billion. So we will be a little torn apart, but you know what? No one will notice. No one will matter. It won't matter to anybody because it happens over such a long amount of time that it wouldn't even be noticed. Okay. Yeah. It's like 2 times wider than we are too. But 2.5 million years ago, what was happening on Earth? Well, there were a lot of major changes on the Earth. The Pleistocene epoch was, leading to the Great Ice Age, which was coming, and really big glaciers in the northern hemisphere were forming. Panama closed up, and basically meant that we were now with the Ice Age. The water level dropped. We had Panama. Wow. We had that Panama, that little Panama Isthmus open up, meaning or get closed off, so the land showed up because the water dropped.
Crazy.
And that changed global ocean currents in our planet, and stopped allowing mixing between the Atlantic and Pacific Oceans.
Wow.
Yeah.
Hey,
and
we're out of time.
Is it really? It's 53. Oh, okay. Well, this will be the last one we do. Okay. It's okay. We're out to the Andromeda Galaxy. This is fantastic. Thank you for letting me know. Mm-hmm. Yeah. And so the first, remember, we're going back in time now. So the first genus of Homo appeared. Homo habilis was prominent. And, we went all the way from 2.5 million years ago to the present day. And that is what was going on here on Earth when the light left those objects. I hope you guys had a really good time tonight. We really enjoyed this. And I want to thank you for your attention. And Tara, thank you very much. Good
Thank you,
night to
Bud.
all of you, and we will talk once again.
Bye, everyone.